So this section is kind of more of the same with limits, except in the last time it was more about the intuitive definitions and trying to understand, what a limit is. Whereas here we're going to kind of go through the rules of what you can do with limits. Now, by the end of this section, you might be wondering, like, what's the point of limits? Because basically, I don't see any different from plugging a number in versus finding the limit. But there is a big difference. So just kind of bear with me as I'm going through this, and I'll try and keep on coming back to the theme of why limits are useful and everything. But so let's just go ahead and get started. The limit of a constant function. So for the function f of x equals c, the limit as x goes to a of f of x. Well, that's the limit as x goes to a of c, and that's going to equal c. Again, if you want to draw a visual representation, if you have a function there, and we have, if that's c, and I have a horizontal line there at c, then let's just call this point a. Then the limit as I approach a, right, as I go from either side. So as I come from the left, it's a, or it's c. From the right, it's c. So the limit has to be c. It's kind of boring. Doesn't seem like there's much going on there, but it's kind of the first step in understanding how this can do it. So as x approaches 8, what does 11 get close to? Well, 11 gets close to 11. As x goes to 0, what does negative 9 get close to? Well, negative 9 gets close to negative 9. Easy enough, right? Now, what if we have the line y equals x? Then the limit as x goes to a of f of x is the limit as x goes to a of x. Now, we can do this visually, or we can just look at this and say, well, as x gets close to a, what does x get close to? So, again, I'm looking at as this x gets close to a, what does this x get close to? Well, as x gets close to a, x gets close to a, right? Again, visually, if you want to look at it, we have this right here. There's y equals x. Here's a. Then as x approaches a, notice from the left and from the right, since it's y equals x, that's a as well. And as x goes to a, x is going, or the y value is getting close to a, which is represented by x. So the limit as x goes to 19 of x is 19. And the limit as x goes to negative square root of 2 of x is negative square root of 2. So far so good. And again, a lot of these rules, basically one of the things when you start calculus, which is what we're doing here, is you got to go like another level of detail as far as, and rigor as far as being clear about everything. So in these, we're just kind of establishing all the rules you can use for limits. Most of them are intuitive. They're things that you think you should be able to do, and here we're just kind of stating that you can. And there are proofs and stuff for all these as well, but we're not going to get into those. So limit as x goes to a of f of x equals L, and limit as x goes to a of g of x equals M. Then this limit is equal to the limit as x goes to a of f of x plus the limit as x goes to a of g of x, which is, again, the first one is L, and the second one is M, so it's L plus M. So the limit of the sum is the sum of the limits, is basically what this one says. So I can look at this guy, and I can say, well, that's the limit as x goes to negative 3 of x, plus the limit as x goes to negative 3 of 16. And from rule number 1, rule number 2, we learned that this one is negative 3. From rule number 1, we know that this one's 16, so I end up with my answer being 13 for this limit. Again, I just reused these two rules in order to do that. Now, whatever works for sums works for differences, because adding or subtracting is just adding the opposite. So I can do the limit as x goes to a of f of x minus limit as x approaches a. My arrows are terrible today, it looks like. Of g of x, so that's going to be L minus M. So that's the limit as x goes to 14 of 19 minus the limit as x goes to 14 of x, which is going to, again, equal the limit as x goes to 14 of 19 is 19. The limit as x goes to 14 of x is 14. So I get 5 as my answer. Now, This next one, again, we don't get, this isn't calculus class, so we don't get quite as into it as you will next year. But um, when we look at this, uh, this limit of a product, this is only true if both of these limits exist. All right. So if that limit were to not exist, if either of those were to not exist, then we can't use this rule. But if they do exist, then we can. So the limit of the product is the product of the limits. So you can almost think of it as distributing that limit, if you will. I mean, it's not quite, because superficially it's similar. And so then I get L times M. So looking at this is the limit as x goes to 7 of -10 times the limit as x goes to 7 of x, which is equal to, the constant is -10. The limit of x is just the x value, so I get -70 as my answer. So eventually we're going to be able to not go through all this additional work, but for now, like early on, I kind of want you to do it just so we can kind of see all the things that we're doing. So step by step, using all those rules that we did. So looking at this, I can say that this is equal to the limit as x goes to -5 of 3 times the limit as x goes to -5 of x, and minus the limit as x goes to -5 of 7. So again, what did I use? Well, for the first part over here, I used the limit of the product there, and then for the second part, I used that limit of a difference. So limit as x goes to -5 of 3 is 3. Limit as x goes to -5 of x is -5. And then limit as x goes to -5 of 7 is 7. So I get -22. Now, limit as x goes to -3 of x squared. Well, that's limit as x goes to -3 times, of 8 times limit as x goes to -3 of x times limit as x goes to -3 of x. And that's going to equal 8 times -3 times -3, which is equal to 72. All right, so now what you might notice is in all of these, basically I got the same answer. Like if I were to plug in x equals 19, I get 19. If I plug in x equals -2, I get -2. If I plug in x equals -3, I get 13. If I plug in x equals 14, I get 5. If I plug in x equals 7, I get -70. If I plug in -5, I get -5 times 3 is -15 minus 7 gives me -22. And I plug in -3, I get -3 squared is 9 times 8 gives me 72. So far, it looks like if I just plug it in, I get my limit. Now, that will be true for a lot of functions, but not all. So remember what we did in the last section when we looked at it graphically. There is a difference between the value of the function and the limit of the function. So far, all our examples we've done today, there hasn't been a difference. But there's a reason for that, and I'll get to that in a little bit. But notice in part B, when we broke this limit as x goes to -3 of x, limit as x goes to -3 of x, notice that's really the same as just having -3 squared, right? So this right here is the same as -3 squared, which would have been the same as just plugging in -3 in for that x value. And we could have done that as many, if it was x to the fifth, it'd be the same thing, right? So basically what this ends up being is if we have a monomial, so just 8x squared is a monomial, it's a polynomial with one term, then basically I can plug in a. So this is going to be b and a to the n. I get to, again, basically just means plug it in. So this is going to equal -7 times -2 to the third, which is 7 times 8, 56. All right, so now notice using this rule that we proved by example. Again, it's we didn't rigorously prove it or anything, but hopefully you can see that it would work. If we take that combined with these limits of sum and difference up here, well, notice f of x and g of x, if they're both both monomials and we add them together, we can just basically plug it into f, plug it into g. So by extension, if f is a polynomial, then the limit as x goes to a of f, or f of x, is going to be f of a. So for polynomials, it happens to be that the limit and the value of the function are the same. That's not true for all of them, but it makes a lot of limits trivial to evaluate. So, but just don't. The problem with this a lot of times is people then say, well, that just, like, what's the point of the limit? If it's the same as just plugging the value, then why do we even consider it? Well, again, this is only true for polynomials, and the reason why it's true for polynomials actually is because they're continuous. Next year you'll learn a better definition of continuity than our intuitive definition of being able to draw it without taking your pencil off the paper. So there are more functions where you can do this. Basically, any continuous function is something that you can do this for. But there are certain functions that we're going to look at actually in the next section that are not continuous, where we want to look at the limit. And so just keep in mind it's a very, 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 very valuable tool, even though right now it just seems like, well, I'm just plugging stuff in. Because that's exactly what I'm going to do for number 8. I'm going to plug in 2. So I get 7 times 2 cubed plus 3 times 2 squared minus 5 times 2 plus 3. So 2 cubed is 8 and gets me 56 plus 12 minus 10 plus 3. So I get 61. And similarly, if we look at this, this is basically using the multiplication rule we learned up above, the product rule, over and over and over and over again. This is the same as limit as x goes to a of f of x to the n, which is equal to L to the n. So if I want to figure out what this guy is, I can find the that's equal to limit as x goes to 4 of 3x minus 5 to the third. And now what I have inside, I mean, 3x minus 5 is still a polynomial if you expand it all, but now what I have inside is polynomial. Plug in 4. 3 times 4 is 12 minus 5 gives me 7, so I get 7 to the third. So 7 times 7 times 7 gives me 343, and that's my answer. And similarly, this works the other way. Basically, one way of thinking of these rules here is that the limit commutes with powers. It commutes with powers. So this is equal to the square root of the limit as x goes to -1 of 6x squared minus 4. And so I can figure out what that limit is, right? That's a polynomial. I can plug it in. I get 6 minus 4, which is 2. So, well, I didn't need that big square root of 2. So let me rewrite that here. No. My eraser wasn't working there. There we go. Again, because of what's in here is just a polynomial, I can just plug it in. All right, and then assuming the limit of g of x is not equal to 0, I can look at it this way. If I can commute with, or if the product rule works, then the division rule, the quotient rule is going to work as well. Basically, it's just, again, the limit commutes with all these operations. The exception on this one is m can't be 0 because we'd be dividing by 0. So find the limit of this quotient. We get that's equal to the limit as x goes to 1 of x squared minus 4x plus 1 over limit as x goes to 1 of 3x minus 5. Again, just using that rule we have up there. Now these are both polynomials, so we can just plug it in. So I get 1 minus 4 is -3, plus 1 is -2. Plug in 1, I get 3 minus 5 is -2. So I get 1 as my answer. So here is basically a table of all the formulas that we've learned so far. Again, basically they're saying all the things that you think you should be able to do with limits that you can actually do those. All right, so now here's a little bit an interesting question. So these last ones are examples where the function might have a different value than the limit. So these are ones where it's not quite as easy as just plugging in. All right, so let's look at the limit as x goes to 1. Remember that little minus sign means from the left. So if we're looking at where as x approaches 1 from the left, notice if we're going to 1 from the left, we're always going to be where x is less than 1. So we're going to use this top function right there. So that's going to equal the limit as x goes to 1 of -1. And again, the limit of a constant is just itself, so I get -1 for my answer there. Now 1 with a plus means we're coming from the right side. So that means we're going to be in this category right here. So I can write limit as x goes to 1 from the right of cube root of 2x minus 1. Now this is again a polynomial in a root, basically means we can plug it all in. So we plug in 1, we get 2 times 1 minus 1 gives me 1, cube root of 1 gives me 1. So I get limit as x goes to 1 from the right is 1. So what's the limit as x goes to 1? Does not exist because a and b don't match. A and b have to match in order for that to happen. So, all right. So these last two, 13 is not too bad. 14 is going to be a little bit different than anything you've done before. And some of the limits can get tough as we get to the end. We don't really get to the really hard ones in this class, but they can get tricky. All right. So looking at this. Find the limit as x equals to 1 of this guy. Now you might be tempted to say, well, that's equal to, from our rule above, limit as x goes to 1 of x squared plus 2x minus 3. Oops, let me make over limit as x goes to 1 of x minus 1. The only problem with this is that, remember, we could only use this rule if the denominator was not equal to 0. So I do that, I get 0 divided by 0. You might say, well, what does that mean? Well, the funny thing is, in the limit sense, 0 over 0 could be anything. 0 over 0 could be infinity. It could be 0. It could be 5. It could be negative pi. It could be whatever we want. It's actually called what's called an indeterminate form. So how do we figure out what this is? Well, think back to our chapter, I think it was way back in chapter 2, how we talked about graphing and how we might have a hole. Well, remember, this is a rational function that has a hole at x equals 1, right? So how would we figure out where that, how to plug that hole in? Well, we would factor it. So we're going to instead ignore all that. We are going to say that is equal to the limit as x goes to 1 of x, looks like we're doing plus 3 x minus 1 over x minus 1. And notice x minus 1 over x minus 1 gets me that. So I get limit as x goes to 1 of x plus 3. Well, what do you know? Now I can take that. That's a polynomial. I get 4. And that's what our limit ends up being. Now that's kind of a powerful tool of the limit, because let's just skip 14 for just a second. I'm going to come down here and write something again. So what we just did was x plus 3, x minus 1 over x minus 1. Now, this statement that I have written right here is incorrect. Okay? Well, you might say, well, wait a second, we just did it up here. But there's a difference. There's a difference. I can say the limit as x goes to 1 of x plus 3, x minus 1 over x minus 1 equals the limit as x goes to 1 of x plus 3. I can say that. So the right side is okay, the left side is not. And the reason for that is, remember what we talked about last time. When we're talking about limits, the value does not, the value of the function, like at the point, doesn't matter. So at x equals 1, it doesn't matter. So notice these two values are true everywhere except at x equals 1, because what is the value of like, or maybe I should be doing it on this side instead. So the values of those two functions are exactly the same except at x equals 1. Because at x equals 1, the left-hand side is undefined, the right-hand side is defined, it's 4. Now, with limits, it doesn't care, when we're saying x approaches 1, we don't care about what happens at 1, right? The limits don't care about what happens at the point, only what happens near the point. So when I slap that limit on both sides, now this is true. This is 100% true. If I want to make the left side true, what I'd have to do is add a little comma, and I'd say x not equal to 1. Now all of a sudden the left side is true. The limit kind of does that for me, and so the limits are equal. And so it doesn't matter what happens at that point. It's going to be equal everywhere around that point. So that's kind of a useful, one of the reasons why the limit is useful. And we'll see the primary reason why the limit is so useful in the next section, where we learn about the derivative. And the derivative is just a limit at its basic level. So last example, find the limit as x goes to 0 of square root of 9 plus x minus 3 over x. Now, your first temptation might be that, well, it's a root, it's division, everything like that, so let's plug in 0. Well, if we plug in 0, I get square root of 9 minus 3 over 0. I get 0 over 0. Well, again, not very helpful. Again, that does not mean it's undefined. The most common mistake here is to say does not exist. But we do not want to do that. Again, the value of the function doesn't exist, but the limit may or may not. So, as you might have guessed from the title here, we're going to actually do something that kind of seems antithetical to everything you've been taught as far as radicals in the numerator and the denominator. We are going to rationalize the numerator. And you'll see why that helps in just a second. So in order to rationalize the numerator, I'm going to have to multiply top and bottom by something. See if while I'm writing this out, if you can think of what that is. All right, so let's multiply top and bottom by the conjugate, right? It's square root of 9 plus x plus 3. Switch the sign. Now when I do that, I'm going to get the limit as x goes to 0. Now square root of 9 plus x times square root of 9 plus x is 9 plus x. The outside and the inside cancel off, and then I get minus 9. So I got 9 plus x minus 9. And on the bottom, I'm just going to leave it like this. You could multiply it through if you want, but I'm just going to leave it like this for now. So notice now I get that's equal to limit as x goes to 0 of x over x square root of 9 plus x. And hopefully now you can kind of see why I didn't multiply it through. Because notice we can cancel those because we're under the limit, so what happens at 0 doesn't really matter. So I can say that's equal to the limit as x approaches 0 of 1 over square root of 9 plus x plus 3. Make sure that's clear, that's a parentheses here. And now I can plug in 0, and notice I get 1 over square root of 9 plus 3, so I get 1/6. So this is one, remember how I said 0 over 0 could be anything? Well, this time 0 over 0 was 1/6. As far as when we're talking about the limit sense. Again, we're talking the limit as something that approaches 0, not actual 0. So a small but important difference. So there is kind of a more in-depth look at limits and how we apply them. Next chapter or next section, we'll be learning about the derivative, where we'll take lots and lots and lots of limits, and they're more similar to what, like number 14, is kind of a more similar example of what we might see than some of the other ones. So, yeah, see you next time.